Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Kabir Nasir Aliyu. I'm here to present direction of arrival estimation based on machine learning with seismic application. My advisor is Dr. Ali Muqaybil, committee members Dr. Sal Darrab, Dr. Wissam Misbah. Okay. I will quickly go over the outline. I have an introduction, problem statement and objectives. I have literature review. I have model for direction of arrival estimation, wireless seismic seismic architecture. I have a simulation result and analysis. I have conclusion and recommendation for future use. Introduction. This research work is divided into three parts. I have a seismic acquisition, machine learning, direction of arrival estimation, which include location estimation. In cable-based seismic acquisition, when I say seismic acquisition, it's a process that is normally carried out by oil and gas companies to determine a new reservoir. So in seismic acquisition, seismic signal is generated in pre-localized source. This signal will go to the earth crust and then it will be reflected by any discontinuity, which will be measured by geophone sensors. This is an electronics devices that normally measure the seismic signal and then transmit it to a storage and processing unit. So if the medium used for the transmission is a cable base, then we call it cable based seismic acquisition. In wireless seismic acquisition, the whole area of acquisition is divided into subnetwork. As you can see now, each subnetwork has a wireless gateway node. This wireless gateway node coordinate certain number of geophones within the subnetwork, and then transmits the signal to a storage and processing unit. So the communication aspect used can be a short range, which is either Zigbee or Bluetooth, or long range using Wi-Fi, MiMax, even though there is a white space, that TV white space. So why did we need wireless seismic acquisition? The main reason is the drawback of the cable base, because about 50% of the cost of exploration goes due to the cabling, and also about 75% of the equipment weight is due to the cable. As you can see, there is a massive scale of cable, and also a lot of time consumption, maintenance, and inflexibility in the system. Another advantage of wireless seismic acquisition is the flexibility of the system. It's highly scalable and higher in productivity, and also there is a reduction in the cost of a crew, and also improvement in the safety and reduce in injury of the injury. So okay, when we talk about direction of arrival estimation, it's a process that is normally used to determine the direction where the received signal is coming from. So this direction of arrival estimation is based on the certain algorithm. So we have different techniques used to determine the direction of arrival of the transmitted signal. So as you can see, we have a beamforming, we have Capon, we have music, we have Esprit, and also we have a recent trend which is called machine learning. That is the recent algorithm used, which is called machine learning. Why did we need direction of arrival estimation in wireless seismic acquisition? One of the reasons is localization of the geophone, because it is very important to geophysicists to find the location of the geophone, and also improve the communication between the geophone and the improve the communication between the sensor node, because this will help in increasing the level of the signal and also avoid interference. When we say machine learning, it's an artificial algorithm that normally learn from a given example so that it can predict unknown example. So based on the arrangement of the neuron in machine learning, we have what is called a neurons. These neurons are arranged in the different layers inside the neural network, inside the machine learning. So based on the arrangement, we can define machine learning deep neural network as a feed-forward neural network, and or we can define it as a recurrent neural network. When we say a feed-forward neural network, it means that, as you can see now, all the connection between the first and the second, there is no feedback. So when there is no feedback between the first neuron and the second node, then we call it a feed-forward neural network. And also we can define neural network based on its learning techniques. We can have a supervised learning techniques. As you can see in supervised learning techniques, we have the input and also we have the target. So whenever you give the neural network the data that it will learn from it, you have to give it a target that the data coming from. Why did we need direction of variable estimation using deep neural network? Because of its real-time response. Even though the training aspect, it has a lot of difficulties, but after the training it can estimate within a few minutes, few seconds, and also less computation in executing tasks, high resolution in predicting solutions, and also wide application. It can deal with many data as you give it to learn. Problem statement and objective. In problem statement, this thesis contribute to the research body that enable the movement from cable base to the wireless, and also applies direction of variable estimation in the context of the wireless seismic acquisition. The algorithm used is a deep neural network. So the main objectives of this research work are review different wireless sensor network that can be used for wireless seismic acquisition, and also review different direction of variable estimation based on the growing trend based on machine learning, and see how we can formulate it in seismic acquisition. And also we have to analyze the robustness of the reviewed algorithm that is using machine learning. Literature review. Wireless seismic acquisition. In wireless seismic acquisition, we have about 10 reviews. Even though we restrict ourselves to only 10, we have more than that. And also in channel model, I like to talk about only 3. Based on direction or variable estimation, I have like 13, and also we have 5 based on least square estimation. Okay. When it comes to the literature review, as you can see here, it's based on wireless seismic acquisition. Jinguel in 2007, he proposed a topology with about 1024 wireless geophone with one data collection center, and also he used 300 to 1000 megahertz communication. He did not even mention the area he used. And also Sabazi in 2008, 2009, up to 2013, he proposed like 4 papers with subnetworks, even though in 2009 he proposed 2-level subnetwork in which it has a wireless gateway node and then data collection center. The wireless geophone used is about 20,000 to 30,000 with spacing along the y-axis 5 meter spacing, and also 10 to 30 meter spacing, but it is a uniform distribution. He used one wireless gateway node for each subnetwork, and also he considered short-range communication within the subnetwork and long-range communication between the wireless gateway node to data collection center. And also in 2011 and 13, he proposed 2 papers which it has the same number of wireless gateway node as it is in 2009, but he increased the level of the network by addition of cluster head in the subnetwork. So in each subnetwork, he has a cluster head that coordinates certain number of geophones. Then he has wireless gateway node that coordinate cluster head. He used short-range communication and long-range communication, and also the area he used about 30 square kilometer. So in 2013, Gokhan he proposed star topology, while in 2016, Jian he proposed linear deployment of wireless geophone, and also Navid and Baron they proposed orthogonal geometry with 30 receiver line. The distance between the receiver line is 200 meter, and each receiver line has about 480 wireless geophone with spacing of 25, and the total number of geophone he used in the system about 14,400. In 2019, Baron he divided the area of the acquisition into a clustered hexagonal cell, and the area each cell has wireless gateway node, and the area he used is about 72 square kilometer. When we look at the channel model, we have Abdul Aziz in 2014, he considered log normal shadowing, and the environment he considered is sand and sparse trees with the shadowing parameter 0 to 7 dB. And also Miranda, he only evaluates path loss exponent in pre-space, building and industrial, while Tajuddin in 2016, he considered log normal in the short and tall environment with shadowing parameter 8 to 10 dB. When we look at direction of arrival estimation and least square estimation, as you can see, on Laschen, he considered neural network with one hidden layer, and the number of sources he considered is about from 1 to 4 sources, and the number of arrays at the receiving end is 5. The search range is from -90 to 90 degree with 10 degree resolution. Casey in 2018, he considered deep neural network with 2 number of sources, and the number of arrays he considered is 5 at the receiving end. The search range is from -60 to 60 degree with 1 degree resolution. Huang and Hu, both they consider deep neural network with 32 number of sources, and the number of array at the receiving end is 128 for both. But in Hu, the number of arrays are arranged in circular form, and also the search range start from -90 to 90 degree with 1 degree resolution, while in Huang he considers 0.01 degree resolution. So when we look at the applying direction of arrival estimation in estimating the position, in the case of least square estimation, Kurt Lewis in 2005, he considered least square estimation for bearing localization, and also Al-Alam, he used angle of arrival in WCDMA system, and also Yassim in 2015, it's an SOB paper, even though he considered a lot of localization aspect in wireless sensor network. And also Musa in 2018, he considered localization via visible light communication system, that is using the angle of arrival in visible light communication to find the position of the transmitter. So when we move to wireless to look at the distribution model, when it comes to wireless geophone distribution model, as you can see here, this is the whole area of the distribution of the seismic acquisition is divided into hexagonal cell. Each cell has a wireless gateway node, which is a triangle. It's a wireless gateway node. Then the wireless geophone, which is a dotted black dot, which is a black dot, are arranged along receiver line. So the distance between the receiver line and the receiver line, which is delta y, and then the distance between the geophone along the receiver line is delta x. So as you can see, YC is used to find the total number of cell in a vertical column, while XC defines the total number of cell we have in the horizontal column. To find the total number of the cell in the acquisition system, we use NR, which gives when the fractional part of XC is less than or equals to 1/3, then we use the first equation, while if it is greater than 1/3, then we use the second equation. So the total number of the cell in the system determine the total number of wireless gateway nodes we have in our model. Sectoring. After we deployed our geophones and wireless gateway node, then we have to apply the method of sectoring to divide the cell into different sectors. So we adopt 3 sectors per cell, and the range of the search range is from -60 to 60 degree, as you can see from this diagram. So the channel model. In the channel model, one of the channel model that we consider is a path loss, and is a log normal shadowing. Log normal shadowing is a path loss which determines the decrease in the power of the transmitted signal as a result of environmental factors and distance between the transmitter and the receiver. So as you can see here from the first equation, is an equation of path loss with a shadowing parameter. The shadowing parameter is a Gaussian random variable with zero mean and the standard deviation sigma. When this shadowing parameter is zero, it has a zero mean and also zero standard deviation, then it goes back to a simple log distance model, which we consider only the distance, the decrease in power as a result of distance. So as you can see here from the diagram, there is a lot of environmental factors that can easily affect the signal. So it's determined by the shadowing parameter. When we look at the Touré model, this is the flat ground model that consider reflection from the ground. That is how the signal is affected as a result of both line of sight and the reflected signal from the ground. As you can see, when we transmit the signal from the transmitter, which is a Jophone, there is a reflected signal that will come to the wireless gateway node, and also there is a line of sight signal. So this signal at the receiving end can be constructive or destructive. If it is constructive, then there is an increase in the amplitude, and while if it is a destructive, then it might result in the loss of the signal. So as you can see here, the reflection coefficient is defined as the modulo square root of the reflection coefficient due to parallel signal, while the second one is due to the perpendicular signal. And also then we define the path loss of Touré model as this equation, which is a 20 log of 4 pi d over lambda, where d is the distance between the transmitter and the receiver, while lambda c is the wavelength of the transmitter signal. When we go to the direction of arrival estimation, so when we go to the direction of arrival estimation formulation, that is the formulation of received signal, let's consider a transmitter, which is a Jophone, wireless Jophone, transmitting signal to arrays, that is in a single sector. Assuming that we have a sector like this, then we assume that wireless Jophone is transmitting signal to these arrays from a far field which is much greater than 2d square over lambda, where d, capital D, is an aperture of the sensor. So the impact of the channel on this transmitter signal is defined as a steering matrix, which is a channel matrix. Then the received signal at any one of these sensors is defined as the product of the channel matrix and the transmitter signal plus the noise in the environment. The noise is additive Gaussian noise, additive white Gaussian noise. And also the vectorial form is given by this, which is x of t, which is this is the vectorial form of the received signal, which is steering matrix, the product of steering matrix, and g of t plus the noise in the system. So in the case of direction of arrival estimation, most of the reviews, after they formulate the received signal, they have to formulate the covariance matrix. This covariance matrix contains the information required to find the angle of the transmitter signal. So to formulate this covariance matrix, we take the transpose of the received signal and multiply it with the received signal itself, and take the mathematical expectation of it. After we take the mathematical expectation, it shows that this is an Hermitian matrix where the diagonal line is a real, and the lower triangular part, they are complex conjugate with the upper triangular part. So since that the lower and the upper triangular part, they are the same, they are similar, then we can take only the lower triangular part and the diagonal matrix to arrange it into a single column vector. This will have the information that is required to find the angle of the transmitter, or the angle of arrival of the received signal. So when we arrange this, then we transpose it, because we are considering at each sensor, then each sensor has its own received signal. Then we take it and we we apply it to a neural network. So that the neural network will learn from this signal, so that whenever he encounter another signal, then he can predict from which angle it is. So least square estimation. After we estimate the angle, then we want to estimate the position of the transmitter. So to find the position of the transmitter, assume that one wireless geophone is transmitting the signal to many wireless gateway nodes. So when we have two wireless gateway nodes receiving signal from one wireless geophone, and we have the estimated angle of this wireless gateway node and their corresponding coordinates, then we can find, this is the coordinate, then we can find the position of the transmitter using this equation. So this is the least square estimation. So here is a schematic diagram of direction of arrival estimation and the position estimation. As you can see, we have the received signal. We convert it into a vectorial form, and also we have the correlation covariance matrix. Then we apply it to algorithm of direction of arrival. Then we estimate the angle. After we estimate the angle, then we use the coordinate of the wireless gateway node. Then we use it in the least square estimation. Then it gives us the position of the transmitter. So the performance metric we use for evaluating the trained network and the evaluation of the position are probability of correct estimation and root mean square. So the probability of correct estimation and root mean square is only for evaluation the trained network, while the mean absolute error and the cumulative distribution function is used to evaluate the accuracy of the position estimated. And result. So in simulating our work, we first start with simulating, that is, we first start with the deployment distribution of the sensors, that is the wireless geophone and also the wireless gateway node. Here is a parameter we use for the distribution of the geophone. We consider two cases of the cell radius, that is 0.8 and 1 kilometer cell radius, and also we consider each receiver line has 480 wireless geophone, and we have total number of 30 receiver line. The distance between the receiver line and the receiver line is given here, and also the distance between the geophones is given here. So each cell has about 450 wireless geophone, and also we have the total area of 72 square kilometer. Total number of geophone is 14,400 as it is proposed by Baron. So here is the simulated version of the proposed orthogonal geometry. Here is the proposed simulation version. So when it comes to a neural network, we first train our network, then we use the trained network and apply it to a seismic acquisition. So the parameter we use for a training network, we consider a feed-forward neural network with a different hidden layer. We first consider one hidden layer, and then we consider two hidden layers. We consider different arrangement of neurons. We have 10 neurons, 20 and 30 neurons. The training algorithm we use a Lombard-Markov train algorithm. So to train the network, we have to generate the training data. This training data has to be generated in similar way with the received signal in the seismic acquisition. So the center frequency we use 600 megahertz. The number of the snapshot is 100, and also the element at the receiving end is 5. The distance between the element is lambda by 2. This is the parameter we use. But in generating the signal, we consider 5 scenarios of the training data. That is 5 scenarios of SNR. So we consider 0 dB SNR, we consider constant. 5 dB SNR, we consider 30 constant dB SNR, consider 0 to 30, 5-step increase. We can also consider 0 to 30 dB, that is 1-step increase. So after we generate all the training data, to give it to the neural network, we define the percentage that the neural network will use for the training and also for the validation. That is to avoid overfitting. So we consider that 80% will be used for the training and the 20% will be used for validation. So here is the result we generated while after we trained the network with 2 hidden layers and 20 neurons. So we try to look how the performance of the network is. This is the probability of correct estimation. So as you can see here, when we train the network using 0 dB SNR, at 0 dB SNR he has a good performance of about 87%. But with the increase in the SNR of the testing data, then the performance decreases. When we train the network using 5 dB SNR, as you can see from the legend, it defines the scenario used for the training, while the x-axis defines the scenario used for testing. So when we train the network with 5 dB SNR, at 5 dB he has a good performance, but away from 5 dB, then the performance is decreasing. And also when we train with 1-step or 5-step increase, you see the performance is also increasing, but it becomes saturated around 8 dB SNR. And also when we check the level of the error in the system, it shows that when we train the network with a constant dB SNR, the error is less. But as the SNR in the training is increasing away from the trained SNR, then the error is increasing as well. In the case of 0 dB, when we train the network with 0 dB, it has a low error compared to the remaining testing SNR scenario. And also, in the case of 1 dB and 5 dB SNR increase, when we train the network with 5 dB increase, as we are moving, the error is decreasing as well because it has a wide range of SNR. Likewise, in 1 dB increase. But when we go back to the probability of correct estimation, when we look at this, you will find that there is a slight difference in the case of 1-step increase SNR. So it shows that with 1-step increase SNR, the network trained with 1-step increase SNR in testing data, it has a good performance compared to the remaining. So after we find that using 2 hidden layers with 20 neurons each hidden layer, it has a good performance, we try to validate this network. Okay. After we find that the neural network trained with 2 hidden layers with 20 neurons in each hidden layer has a good performance, then we try to validate this neural by making a comparative evaluation with other neural networks. We start with 1 hidden layer, 10 neurons in the hidden layer. The probability of correct estimation shows that at 0 dB SNR, even though because we use the testing data, it has a range from 0 to 30 dB SNR with 1-step increase. So we try to test it. We try to test the neural network with 1 hidden layer, 20 neurons. It shows that only 70% can be estimated at 0 dB, then the performance increase. But when we increase the number of neurons in the hidden layer to 20, the performance at 0 dB moved to like around 85%. But with the increase in the hidden layer with 10 neurons each hidden layer, the performance moved to about 86 or 88 or 85. Or 87 if I can say. So it moves to around 87% at 0 dB SNR. But with the increase in the neurons, the performance also increased with slight lead using 2 hidden layers with 20 neurons per hidden layer. But to evaluate the amount of the error in the system, when we look at the root mean square error, we find that with 2 hidden layer, 20 neuron each hidden layer, it has a good performance, better than the remaining configuration of the neural network, as you can see from this figure. Okay, also, so since that we have understand using 2 hidden layers with 20 neurons have a better performance, then we use it for localization in the seismic. So to apply it to a seismic acquisition, we have to generate a seismic signal. That is, we have to allow the geophone to transmit the signal after we deploy it. So as you can see here, that each geophone is transmitting signal with 600 megahertz, even though we consider 2 cases in this. We consider using 600 megahertz, and then we move to a higher frequency, that is 2.4 gigahertz. So the snapshot we use is 100 as it is before, and also the power of the initial power of the transmitted signal is 40 dBm. And also we consider 1 meter, close reference distance with the path loss exponent of 2, and also the shadowing parameter we consider from 0 to 7 dB. So results. When we look at the performance evaluation of localization, we try to estimate the position of the transmitter using 2 wireless gateway node, 3 wireless gateway node, 4 wireless gateway node, up to 8 wireless gateway node. So as you can see here, with 1 kilometer cell radius, 0 dB, that is a solid red line. With two wireless gateway node, the performance is about almost 2 point something. It's about almost 2.3, but the performance also increase, that is the error decrease with increase in the number of wireless gateway node, up to 4 wireless gateway node. So after 4 wireless gateway node, then the performance decrease. Why? Because we are increasing the number of wireless gateway nodes that are far away from the transmitter. That is, we are taking closest wireless gateway node. So as we are increasing the number of wireless gateway node, we are like accumulating with the wireless gateway nodes that are far away from the transmitter. So, but when we decrease the cell radius to 0.8 kilometer, you see the dotted line, the dashed line, you see the performance decreased to 1.2 using 2 wireless gateway node. And then when we increase the number of wireless gateway nodes, the performance almost goes to 0.0 something, which is about 0.03. Also, then the performance decrease with an increase in number of wireless gateway nodes in the estimation process. But when we look at the total number of the wireless gateway nodes that we can be able to, wireless geophone, the total number of wireless geophone that we can be able to estimate using different configuration of wireless gateway node used for the position estimation, we can see that with 1 kilometer cell radius, 2 wireless gateway node have about 73%. That is, 73% of the wireless geophone can be estimated within 1 meter away from the actual position. But with decrease in the cell radius, the performance moved to about 82%. So also, when we use 4 wireless gateway node in 1 kilometer cell radius, we have about 84. But with decrease in the cell radius, we have about 91. So this shows that decrease in the cell radius increase the performance accuracy, because when we decrease the cell radius, the distance between the transmitter and the wireless and the receiver, that is the wireless gateway node, decrease, which shows that there is the wireless gateway node receives signal with high SNR. So in the previous slide, we understand that 4 wireless gateway node has a best performance accuracy. So we try to use the 4 wireless gateway node with varying of shadowing parameter in the system. So when we use 1 kilometer with 0 dB shadowing parameter, as you can see here, we have about 82% of the wireless geophone can be estimated within 1 meter away from the actual position. But when we increase the shadowing parameter to 7 in 1 kilometer cell radius, you can see the performance decreased to 49%. Only 49% of the wireless geophone can be estimated within 1 kilometer. Likewise, when we decrease the cell radius, that is using 0 dB, we have about 90% of the geophone can be estimated within 1 kilometer. But when we increase the shadowing parameter, then the performance moved to like 67%. So it shows that with the increase in the shadowing parameter in the system, in the environment, the performance decreased because the transmitter signal is affected by many factors in the environment. So in trying to move to a high frequency, which is about like 2.4 gigahertz, the length covered by the signal will decrease because of the increase in the frequency. So with the decrease in the length between the transmitter and the receiver, so we consider 1 meter cell radius. So after we simulate with the given parameter above, we find that a lot of wireless gateway nodes appear in the system, and some of them they are not even serving wireless geophone. If I can say, they are live without doing anything. They are there without doing anything. So this makes us to adopt a linear deployment of wireless gateway node along the receiver lines, as you can see in the next in this figure. So this is the linear deployment of wireless gateway node, as you can see. So in trying to look how the estimation of the position of the wireless geophone can be done using our trained network, we try to look to generate the seismic signal and test the estimation of the position and see how the performance accuracy is. So when we look at this, it's an mean absolute error in the linear deployment. So as you can see, with 2 wireless gateway nodes in linear deployment, the performance and also with 2 wireless gateway node and increase in shadowing parameter, you see we have 0 dB. So the performance is about almost 12 meter mean absolute error. But with the increase in the wireless gateway node, then the performance increase. Likewise in 3 dB and also 5 dB. With increase in number of wireless gateway node in the estimation process, this helps in decreasing the error in the estimation. When we look at the CDF, that is the percentage of the wireless geophone that we can be able to estimate with the configuration of wireless, that is the number of wireless gateway nodes used in the estimation process. As you can see, 5 wireless gate, we consider 0 dB. We consider only 0 dB shadowing parameter. So you can see that 5 wireless gateway node and 4 wireless gateway node have similar performance, about 91% here, about 91%. So it means that 91% of the wireless geophone, that is deployed wireless geophone, can be estimated within 0.6 away from the actual position. So we have like error of 0.6. If we deploy it in 0, in position of 0, then it can be estimated away from the actual position by 0.6. And also, when we increase the number of the wireless gateway node to 6, as you can see, the performance decrease, because we are accumulating with the wireless gateway that are far away from the transmitter. So it means that with the increase in wireless gateway node in the system, starting from 2 to 3, the performance increase. But after 5 wireless gateway node, then the performance will decrease. When we look, so we find that 5 wireless gateway node give a best performance of estimation. So we try to fix the we try to look at how the variation of shadowing parameter in the estimation process or in the environment affects the estimation process. As you can see here, when we consider 3 dB shadowing parameter with 3 wireless gateway node, it shows that only about 80% of the wireless geophone can be estimated within 0.5. But with the increase in number of wireless gateway node, then the performance moved to around 86%. So about 86% can be estimated within 0.5 using 5 wireless gateway node. Also, when we increase the shadowing in the system using 3 wireless gateway node, only 80% can be estimated within 0.5, but with the increase in the number of wireless gateway node, the performance moved to like 82%. So it shows that even with the increase in the shadowing parameter, 5 wireless gateway node, increase in the number of wireless gateway node improves the performance of the estimation process. So here is the result of the two-ray model. We try to simulate the two-ray model, even though we are still working on it. It shows that when we consider the two-ray model, 5 wireless gateway node can provide a good performance estimation of about 91% of the deployed geophone can be estimated within 0.4, as you can see here, within 0.4 away from the actual position. Then the performance decrease. That is, so it shows that with the increase in the number of wireless gateway node in the estimation process, the performance also increase, because we start from 2, then the performance increase when we consider 3, then the performance also increase when we consider 4 and 5 wireless gateway node. So on conclusion, we simulate orthogonal geometry in wireless seismic acquisition, and also we consider linear deployment in wireless seismic acquisition. The network assets used to provide is a hexagonal cell with wireless gateway node per cell, and also we introduce a deep neural network for directional arrival estimation, and we test its performance. And also we use least square estimation to estimate the position of the transmitter in different channel conditions. And also the result shows that in the orthogonal geometry, 4 wireless gateway node, or if I can say in the all 4 wireless gateway node, is enough to estimate with high accuracy. And also increase in the cell deteriorate the estimation accuracy. So the increase or decrease in the cell affect the performance, that is the estimation accuracy in the system. So some of the recommendation is we would like to look over how the 2 wireless gateway node, 2 or more wireless gateway node, 2 or more wireless geophone can be considered in the system, and also we like to make a comparative between different machine learning algorithms, and also we like to evaluate different localization algorithms with the directional arrival estimation in the context of seismic acquisition. Some of the directional arrival estimation we would like to use like receive signal strength, time of arrival, and time difference of arrival. And also we like to improve the localization accuracy using map-aware localization techniques, and also we like to use real experimental geophone and wireless gateway node to see how they can apply the directional arrival estimation and positioning estimation. Thank you very much. Assalamu alaikum.